Now we're going to look at the network facility location problem, where instead of looking on a continuous space and finding one location out of any possible location, we're going to have candidates to select from. So the objective is very similar still. We want to find the location or locations from a list of candidates rather than a continuous space that minimizes the total costs of delivering from this point to the n or k different destination points over a given network. So this is almost identical to the problem statement we had before. The difference is we have a list of candidates now. So how are we going to solve this? We're going to use a mixed integer linear program. And so what I'm showing you here is the formulation. Calm down. It's not that complicated. Let's break it down. We know it's a math program because we see the objective function and we see that we're minimizing something. We see we're subject to a series of constraints. So, okay, I know where I am. So now let's look at it a little more because it shouldn't be that unfamiliar to you. Because in fact, this is the transportation problem with some extra constraints. We've still got the objective function that's minimizing the cost of the flows, the Cij's times the Xij's, which is what we did last time. We still have these supply constraints that's making sure that everything from the source nodes doesn't exceed what I have available there for all the I's within the supply set. I'm doing the same thing on the demand side, right? Where I'm looking for all the flow going into each of the J locations for that are in the demand set, that they have to be at least as much as what was demanded. So this is the exact same formulation as we had for the transportation problem, along with our non-negativity constraints for the flows. I can't flow negative volume. The only thing we're doing is adding some constraints. So let's talk about those, and we'll start from the bottom. I'm introducing a new decision variable, this y. Y sub I is a binary variable. That means it can only take two values, either 0 or 1. It's not between 0 and 1, it's either 0 or 1. We use this to indicate whether to open or not open a facility. So y sub I is equal to 1 if distribution center I is opened. Otherwise, it's equal to 0. And this is for all the I's that are in the supply set. Okay, so that's the first one. Now, we might want to have a set of constraints that limit the number of facilities I open. And so I'm introducing two new constraints here. One is setting a minimum value, P min, which is an input value I give, and then an upper bound, P max. So P is the number of facilities I can open, min is the lower bound, max is the upper bound. How do I enforce that? Well, I'm simply going to sum all of the y sub i's. So if I sum those up, since it's 1 if it's open, 0 if it's closed, if I sum all the y sub i's up, that's the number of facilities I'm opening. And so these two constraints just set the min and the max. Make sure I fall within those two numbers. Pretty straightforward. All right, now let me go to the top because we've added something to the objective function. And what is this? Well, I've got this y sub I, right? That's the decision whether I open a facility or not. It's a binary variable, and I'm multiplying it by this f sub I. And that's simply the fixed cost for opening DCI. So this problem that we did, that we're looking at, this could be for flow over the course of a week, a month, a year. And so this fixed cost is the cost for opening this facility for that period of time. So it could be labor, it could be lease, it could be any kind of thing that doesn't change with the amount of volume going through. So the f sub I is independent of how much volume is going through. If I have 1 unit going through, I pay the same amount. If I have 1,000 units going through, I pay the same amount. So it's a fixed cost with respect to the volume flowing through it. So I've got two elements to my objective function now. I have these variable transportation costs that I'm circling, and then I've got these fixed facility location costs. So variable costs are based on the flow. The facility costs are based on the locations that I open. All right, we're almost there. We have one other constraint that I need to talk about, and that's this one. Because up until this point, I have two decision variables, or two types of decision variables, the flow and the locations, and they're totally independent. If I didn't include this logical or linking constraint, what would happen? Well, the X's would do whatever they needed to do, just like in the transportation problem. They'd solve the demand, make sure I met that and didn't exceed supply. but the y's would stay at 0. In other words, if I didn't have something connecting them together, then this would just be the transportation problem all over again. It would say, okay, all facilities are open, they're all free. So we need something to tie together the x's and the y's. So here's the same formulation. I just made it a little smaller, and I boxed the constraint we're going to talk about, this linking constraint. And so what does this mean? Well, what this is really doing is saying we can't deliver from a distribution center unless that distribution center is open. Because if we don't do this, then the objective function right here is going to force it closed. It's going to say, hey, it costs me money to open it. If I don't have to, I won't. What if it's not included? Well, we kind of talked about this. It becomes a transportation problem. If this constraint is not here, right, if we got rid of it, you essentially have the transportation problem, and there's nothing different. But it is here, and so let's talk about why it works. Okay, so let's think about it, because all that it's saying is that any flows I have from I to j, and so I have node I, and it's going to node j. If there's any flow on here, right, then we want to make sure that I is turned on, that y sub I is turned on. So what if xij is 0? What value will y take if xij is 0? Well, if it's 0, then I'd have 0 minus this m, and we'll talk about it, but just assume right now it's a really big number. So 0 minus a big number times y less than or equal to 0. So y could actually be any number at all, and it would satisfy this constraint, which means that y, it would be forced down to 0. So if there's no flow, then it's going to go to 0. However, what happens if I have 1 unit of flow going through? Just 1 unit. So now it would be 1 minus big number m times y has to be less than or equal to 0. What value does y have to take? It has to become 1. It can't be 0 anymore. It has to be turned on. So what this constraint is doing, it's forcing, by keeping it in negative, it's saying if xij is positive, then yi has to be 1. Or if not, then it won't be less than 0. Play with this and see how it works. It's a very clever constraint. What's the best value for these m's? Well, as a general rule, you want it to be big. But technically, you don't want to make it too big, because then it slows down some of the solution time, and it takes a little more effort. So a good rule of thumb, you set the mij greater than any value that the xij, the flow, can possibly take. In fact, it's okay, it's perfectly acceptable to set all the mij's to the same number. You set it equal to the sum of all the demand, right? Because the flow on each individual arc can never be greater than the total demand required. So that's one way to do it. Just set a really big M, and that's why we make it just a big M. I'll talk later about how you can make that a little more finer, because it makes the solution a little faster. But it's perfectly acceptable to set the M just to make it a really big number, because what you really want to do is connect the x's and the y's. So what we're going to do next is put this into a spreadsheet, and we're going to solve it.